Vibration analysis. Procedures for accurate evaluation of machinery condition. Theory. The measured frequency tells what is wrong with a machine, and amplitude identifies the relative severity. Frequencies do not lie, although they can be misunderstood, measured improperly, or interpreted incorrectly. Amplitude, on the other hand, can be over or understated. Amplitude is not understood by most people and is often misinterpreted. For these reasons, amplitude, all by itself, is of little value and should not be relied upon. For example, a small fan could vibrate at levels up to 1 inch per second for years and not fail. On the other hand, a bearing with a cracked inner race could fail within days with an amplitude of 0.02 inch per second. Most of the vibration severity charts were designed for imbalance only. However, over the years these charts have been used and applied to all machinery problems. The net result is that machines fail, and the vibration level does not go up, in fact it often goes down. Consequently, people think it is a catastrophic failure. If diagnostics had been performed along with or instead of condition monitoring, some warning would have been obtained. Figure 1 is the balance tolerance nomograph, which contains a good balancing specification for rigid rotors during shop balancing. When using this graph, place one end of a straightedge on the rotor weight scale and place the other end on the rotor operational speed scale. Then read the allowable gram-inches of residual imbalance from the intersection of the straightedge and the center scale. This graph is based on IS 0-1940 and ANSI IS 2.19-1975 with some refinements. Figure 2 contains the operating machinery imbalance guide. This chart is a good guide for general severity of imbalance only. We do not know the origin of this chart. However, it may be a derivative of the Rathbone chart. Various versions have been published in several places. In some circles it is referred to as the IRD chart. Regardless of who deserves the credit, it is a good chart for imbalance severity and should not be used for other problems. Some frequencies are permitted at acceptable levels in some machines. Some examples are imbalance or one-time RPM, gear mesh frequency, vane pass frequency, etc. These frequencies should not contain harmonics, except for one-time RPM and fluid film bearings, modulation, or truncation. In other words, a good machine could have the above discrete frequencies at amplitudes of less than 0.2 inch per second. Other frequencies are not permitted at any level within the prescribed calibration levels. Some examples of these frequencies are oil whirl, all bearing frequencies, pulses, except in cutters, etc., noise, and fractional discrete frequencies. Most real-time analyzers have enough sensitivity to measure the balls or rollers passing under the transducer. If the calibration standards are not observed, or if auto-ranging is used, bearing frequencies could be observed without the presence of a significant defect. Previously, we have discussed how frequencies add, subtract, modulate, and truncate based on physics in an electronic environment. Sometimes rotating machines can behave in a very similar manner. A good example is a beat. If a 1776 RPM motor was belt driving a 1500 RPM fan, and the motor and fan were isolated from each other, the motor would be vibrating at a frequency of 29.6 Hz, and the fan would be vibrating at a frequency of 25 Hz. This is true when there is no mechanism to allow the two frequencies to beat. If the motor was mounted on the fan pedestal, then the two frequencies could beat. The flexibility of the fan pedestal is the mechanism that permits the two frequencies to beat. If the fan and motor mounting were isolated and the motor was loose, the beat would be felt on the motor and not on the fan. If the fan was loose, the beat would be felt on the fan and not on the motor. In both cases, the looseness is the mechanism that permits the beat. In these examples, the nonlinearity or looseness and flexibility in this case permitted the frequencies to beat. In other cases, two frequencies can be present, generated by the same machine, and they will not beat. An example would be imbalance and vane pass frequency. In such cases, a spectral line is present at rotating speed, and another spectral line is present at vane pass frequency. In this case, we have two frequencies in two problems or imbalance and a vane pass frequency problem. The time signal is that of a high frequency riding a low frequency. On the other hand, if the impeller was loose on the shaft, the spectral line at vane pass frequency could be modulated by unit speed. Modulations of speed could appear below and above vein pass frequency. However, more energy may be contained in the sidebands below vein pass frequency. Sidebands below the discrete frequency are in out-of-phase condition or looseness, and sidebands above are in in-phase condition or eccentricity. In some looseness problems, sidebands can occur on the high side when eccentricity is not present. This occurs because looseness goes in and out of phase. Remember, if frequencies are out of phase, they subtract; if they are in phase, they add. In either case, amplitude modulation occurs. In other cases, the various frequencies are not generated and then added together. In these cases, only the resultant time signal is produced. Remember, a perfect sinusoid contains only a discrete frequency. The only way to distort the sinusoid is to add some harmonic content. The distorted signal can take many forms, depending upon the harmonic content and the phase relationship of the harmonics. This signal is normally the discrete or fundamental frequency along with various harmonics and their phase relationships. Since phase is not presented or is discarded after the fast Fourier transform or FFT is performed, the time signal must be used to obtain phase for accurate diagnosis. If your analysis does not include the time signal, your diagnosis could contain up to a 20% error rate. Thank you.